In the third lab experiment, we will compute the pulse rate from a PPG signal as well as the pitch period of a speech signal using an autocorrelation function. So what is an autocorrelation function? Well, an autocorrelation function is just a function which is a multiplication of a signal with itself with certain amount of delay. So the formula is just this: summation of m is equal to minus infinity to infinity xm multiplied by xm minus k. So what that means is this particular sequence of that signal is shifted in time by a factor of k, and then it's multiplied by the original signal. So the autocorrelation function is basically used in cases where you have to find out the distance between objects. So an example of that can be a submarine, right? So a submarine sends a particular signal and it takes time for it to receive it back. So but how does it know what signal it's receiving? So if it sends a signal of a particular frequency, only when it gets a signal of the same frequency back will it get a very high signal. So this is one of the practical applications of a autocorrelation function. Now the normalized autocorrelation function is just the same autocorrelation function divided by the maximum value, which is the value at 0. The reason why this is a normalization is because this value, unless it's an infinite sequence, will be maximum at what k is equal to 0, because that gives you the energy of the signal, the x signal or any input signal that you have. Now, what are the properties of the autocorrelation function? So, since you're just multiplying the signal by a time delayed version of itself, either when you move it forward or when you move it backward, you'll get the same signal back, right? Hence, it's symmetric about the y-axis. And like we discussed before, the max value is at the origin itself. Now, one very interesting property is that if the data has a period of t, even the autocorrelation of the data also has a period of t. Now, this can be intuitively visualized. Imagine you have a signal of an infinite duration. Imagine you have two sine waves of infinite duration. Let's look at figure 1. So in figure 1, both of them are exactly correlated. They are perfectly in phase. So in this case, the autocorrelation at, let's assume k is equal to 0, because there is no time shift, right? Although it's an infinite signal, let's just assume that this is at k is equal to 0. Here you'll get a perfect energy signal back, right? It becomes the same case as before, which is rxx0. Now, let's assume you shift one signal by about pi by 2. So what does that give you? When you shift a particular signal by exactly pi by 2, both one wave becomes a perfect sine wave and the other wave becomes a cos function. So if you multiply this in an infinite duration and you integrate over that, or you sum over that depending on whether you're using a discrete or a continuous time frame, you will get a value of 0. Now looking at figure 3, these are perfectly out of phase signals, right? So you'll get, when you do this autocorrelation, which is where you have shifted this particular signal by a time factor of minus pi or plus pi, depending on how you're going to see it, you will get a value of -1, which is a negative phase. Now when you shift it by 3 pi by 2, either plus or minus again, you will again get a 0 value, and when you shift it by 2 pi, you will get back the same value as you got in figure 1. So as you can see, when you transition from a period of 0 to 2 pi, you are getting a signal that is bound to repeat. So through this intuitive thought experiment, you can see that the autocorrelation just will give you the time period of the original signal. But in reality, the autocorrelation function, like if we plot it in MATLAB, we get something like this. The reason for this is because the autocorrelation of the functions we do are of functions that are not of infinite time, they are of finite time. So what happens is, when there are two signals and you're multiplying them with each other, initially it's going to be a very small value, right? Because you have time shifted to a point where it's almost, if it's near 0, or just like the first value you're multiplying. So as you start moving, sorry. So as you start moving one signal from a negative infinity to a positive infinity, you'll have a series of zeros when suddenly it finds this particular signal at a particular duration and starts getting multiplied. So there will be a point where at k is equal to 0, where you get an infinity, and then again say the signal is of finite duration. There's no multiplication after that, right? There is no infinite data values for it to multiply. So any value after a particular, say, time instance, the values become 0. Hence, there's a decrement here. However, you can still see that it is periodic. And if there is some inherent frequency or inherent periodicity in the original signal, irrespective of the amplitude uh, diminishing over time, you will still get a period. So a time difference between this and this would give you the period back again. So now what the main goal, what we want to achieve is we want to find out the time period of a PPG signal, and using that time period we're going to get the frequency. So how are we going to calculate the time period? Well, this is a bit intuitive, so we can just look at this figure to understand that. What we're going to do is we're going to first find the autocorrelation, which will get some figure like this, or even if we take this particular part, this half, which, sorry, I'll just go down here. You take this half, which corresponds to this half. You would get the time period by just subtracting this time that we have got this particular signal minus the time we have got this particular signal. Now, how would we actually get this? Well, what we're going to do is once we calculate the autocorrelation, we need the second maxima, right? Because once we have the time value where we got the second maxima, we can subtract it from the 0 point and we can easily get the time period. So so after finding the first maxima, we try to find out the points of zero crossing by normalizing it. I mean, we get a zero mean signal first, and then we try to find out the first point where the zero is crossed. So we'll get some value here because this line corresponds to 0 and it crosses the 0 here. So so if you find the next maxima after the 0 crossing, which will obviously be this, you can easily get this time duration and then find the time period. But since we are working with discrete data points, in reality we don't get the time frame as such, we just get the data point. So once we get the data point, all you have to do is multiply by the sampling frequency, and once you multiply by the sampling frequency, you get the time period. Now the pulse rate is calculated as 60 divided by TP, which is just the rate of your heartbeat, which is in beats per minute. So in our code, we have done more or less the same process as I explained earlier, but we have around 2000 samples. So actually 2000 samples might be difficult for a few processing systems to process. Hence, we divide this into 4 windows of 500 samples. Sorry. Now, after we get these 500, the window of these 500 samples, we pass this data through a moving average filter, and also pass the data through no filter as such. This is actually done so that we understand how the filtering process affects the calculation of the time period and therefore the pulse rate. And what we actually notice is that after passing through a moving average filter, it is better for you to calculate the pulse rate as well as time period, because your pulse rate that you have is not of a very high frequency. Hence, if you want to remove the high frequency components that may change your measurement, we can pass it through a low pass filter, which is again a moving average filter, like we had explained in the first experiment. So let's come to the code. So initially this is just defining the data, and this test data is just for a 500 window, and the working data is just defined again for an array that we're going to use eventually. Now so what we initially do is, since we want to divide it into a window of 500 data points, we make sure that the test data as well as working data are populated with these data points, and we also calculate this average. Just note that this is just for the computation of the non-filtered part. The filtering part is done as a different piece of code, which is again done in the following code block itself. So once you populate these data points, what you do is you subtract the average of that. The reason you do that is, like I said before, you need a zero crossing somewhere, right? But imagine if you don't have a zero mean signal, all of this entire graph can be more than your 0 point. So hence you will not be able to compute the zero crossing that you want, and you will not be able to get the second maxima that way. There are other methods like finite difference or something which you can use to get that second maxima, but since we are going with this method, it is more prudent to subtract the average. So once we do get the working data, what this code block does is it finds the autocorrelation of that. So what this does is it has two loops. One is the outer loop that runs for 500 samples, and one is the inner loop that also runs for 500 samples. And initially x is defined to 0. So what this does is it just looks at one particular data point and subtracts the ith position value from that current working data just to get the autocorrelation. So what that is doing is sorry. So what this basically does is once this is see, if you can just look at this particular part, this multiplication, all it's doing is looking back I samples back, right? So this I corresponds to the k that we're looking at, which is the k that we're looking at, and this j, this particular loop, all it does is it does the summation from minus infinity to infinity. But in our case, since we have only a finite length of samples, it is from 0 to 500, and we are only looking at one particular site, not a symmetric signal. So since this is only delaying it by ith samples, you can easily see that this gives you the autocorrelation, and we are just storing this in a particular array for just for the sake of computation. Now we have to find out the zero crossing, right? So this particular code block does the same. So how do you find out the zero crossing? So for one intelligent method of doing that is you look at a current data and then look at the data just after that. If the multiplication of both of them gives you a positive value, that means that both of them are positive and hence lie on this part of the graph until it reaches the first zero crossing. But once there is a new data point that is negative and the previous data point is positive, the multiplication that will give you a negative value, and hence you'll be able to know that that was the location where the zero crossing was. The reason why this is a better method is a better method than actually checking for zeros in your autocorrelation function is because there is a possibility that you have a data point here and a data point here. There may be a case where you have no zeros anywhere in your data if the data of your autocorrelation function. However, you might have to interpolate this signal to get that zero crossing. So since we're not interested in doing any interpolation, we assume that if there is a multiplication between two samples, the zero crossing happens at the part where it becomes at the first negative, because we don't need the exact zero crossing, we just need a reference after which we're going to look at the maxima. Hence we use this process. So once you do this, all you look at is we get the location of the second maxima, and once you have you have the location of your zero, and now you want to find the second maxima, right? So to find the value of your second maxima, all you do is you start from that particular zero crossing and then keep moving on till you get the maxima. So this code block just does that. It keeps on checking for the maximum value from a range of the first zero crossing and till the end of the data, and if it finds any maximum value, it will replace the original max value with that, and the location which is pre-filter maxima with that, with the location of data. So now since you have the location of data as well as the second maximum value, you essentially have the location of where you get a second maximum. Now the same thing is done for the second case also. However, the only difference is that it is first passed through a moving average filter, and then the zero mean is subtracted from that. And since we've already explained the moving average filter, I'm not going to go through it again. Now, all of these code blocks more or less do the same thing as the one I have explained before. and this is just for printing them. So the Arduino code, the plot you can get from the Arduino code is just this, where you can see that the signal goes down and again becomes a peak, and again goes down and again becomes a peak. So you can see it's a periodic signal which is diminishing because of the finiteness of the signal. And you can see that non-filtered as well as filtered PPG has not much of difference, but there only in one particular reading do you have some error. And this will be more accurate than this because this is actually filtered and we don't want the high frequency components as explained before. Now the same thing is done for a speech signal also, but in this case you calculate the pitch as 1 by pitch period, and the pitch period is calculated the same way as the time period as before, which is index number of points of second maximum plus 1 into the sampling frequency. Now the code remains the same, however in this case we have 4000 data points, and we have just used 500 windows of these 4000 data points to get our data, and the code more or less remains the same other than a few edits here in the end. And that is because we have to divide this by the frequency, right, which is this, which is this. So your sampling frequency is 8000 hertz, and therefore we divide this by 8000 hertz. And now the plots derived from the Arduino code are just this, and you can see that the red function in this case is giving you a much smoother autocorrelation as compared to the blue one, which is the unfiltered one. And this again is a repetitive signal as we have seen before. Now the fundamental frequency values that we have got are 148, 153.85 and so on, and these values have been calculated with respect to the smooth signal, which is the red color, and the average is on 147.57, which is well within the range. So I think that is the end of my video. Thank you for your time.